So my name is Dhruva. We are Team Mechanicis, and this is a presentation of basically our work for the RoboCupJunior Rescue Simulation 2023 competition. So my name is Dhruva. I was responsible for the SLAM portion of our presentation and competition.
Yeah, and I'm Peter Leong. I was responsible for the navigation and mapping, and we have two other teammates, Andrew Chen and Andrew Dai. They were responsible for victim detection and quality assurance and testing.
We'll go over that. So problem statement.
Yeah, so this is what an example maze will look like. So it's split up into 4 rooms. So you can see on the top right, this is what a room 1 will look like. It has basic walls. You can see there are obstacles. There are swamps, those tan tiles, there are black holes. As we move down, there's a blue tile connecting these 2 rooms, and we move into room 2. Room 2 also has full-size walls, but it also has half-size walls. And then as we move into room 3 with this purple tile, we have full-size walls, half-size walls, and now we have curved walls. And then once we get into room 4 with the red tile, we have basically anything goes here. You can have any size walls, anything, like those weird formations there. Also we have victim and hazmat signs on the walls. You can see there's an H, there's some small, there's the red one, there's the U there. And basically the robot has to correctly identify that there's a victim or hazard and has to identify like which type. So whether it's an H, S, or U, and whatnot.
So the colored tiles just to indicate they're going from one room to another, or it's actually a ramp or something?
Yes, it's just the color.
Yeah.
You never get a ramp of the
No ramps.
Okay.
All right. We have a virtual robot here because this is all in a simulation, so there's no need to actually build anything. It's all free, the simulation platform. It's open source, you can just download it, and then there's another there's a thing called Erebus, and that's what takes control of the competition side with all the scoring and stuff. So on our robot, we have 2 motors, left and right. We have a GPS that's for determining the position throughout the maze. We also need to return the position when we detect victims and hazards. We have an IMU for the rotation of the robot. So that's for accurate turning. The LiDAR, it's for seeing the walls. It's very helpful when Dhruva is going to talk about his room for navigation. On both sides of the robot, we have cameras. That's for detecting our victims and hazards. And then on the bottom, we have an additional camera, and that's for seeing what color the floor is. So that's useful when we want to avoid the black holes and seeing the colors on the ground. It's all simulated, so we don't need to build anything. Yeah, there's a website where it's standardized, but you get to choose what sensors and where the positioning is.
Yeah, and you have a budget, like I guess a virtual budget, and if you only have like a certain number of sensors and motors you can like add to the robot.
Oh, really?
Yeah.
So is that a typical robot that you would use in the maze, or the physical one?
Yeah, so this is like called an epoch. It's like pretty standard. They come in like actual, like it is an actual robot that you can like buy right now or make yourself. But I mean the sensors that we've attached, they're just sort of like boxes. We haven't done any actual like hardware.
Well, I mean, there are 2 wheels on that robot. Only 2 wheels, so it doesn't. What?
Yeah, I mean, no, in the simulated environment, it's like pretty stable.
You can't see it in the real one. There's a 3rd wheel on the back, which is there for support. Okay, in the real. Okay, the real one. Yeah.
Yeah, the neat thing is, even though it's simulated, we could, if we wanted to, we could use the same kind of code, and then if we built the same robot, we could kind of just ported over.
Did you try?
No, we didn't.
LiDARs are actually really expensive to
Yeah.
buy and stuff, so that's why this is nice. You get the capability of using one, but you don't have to buy pockets for it.
All right, so first I'll talk about our navigation. We use the breadth first search algorithm, and that's for finding the shortest path to our next unvisited tile. So in this diagram here, this green tile is our current location, and let's say this red tile is where we haven't visited yet. So the goal of this competition is just to traverse as much as we can. So that's why we want to mark tiles as unvisited and visited so that we can try to go to what we haven't seen yet. So first, what we do is we want to try to find our neighbors. And what we define as a neighbor is an adjacent tile that's not blocked by any walls. So if we're starting at 5, the only neighbor we have is 8 because 2 and 4 are blocked off by walls. And then we could just find the neighbors of the neighbors that we found. So once we found 5, we found 8 for that. And then 8, we get 7. We don't add 5 again because that's our source. So we already found that. And then 7, 4 is our neighbor. We don't add 8 because 8 was already found. And then 4, we get 1 and 3. And then we go to 1, we find 0 and 2. And then 3, the only neighbor here is 6. And since 6 is our unvisited tile, we return that, and that's where we want to go. At the same time, we're marking the source tile, so where we came from, so that when we want to actually travel to the tile 6 here, we know how to backtrack so that we can actually move between the tiles to find the shortest path. So in this case, since we marked the source of each tile, 6 came from 3, 3 came from 4, 7 and 8, we just go back. So we're starting at 5. Since 6 isn't like directly connected to 5, we want to go to the parent, the source of each tile until we get back to 5. So we just go back 6, 3, 4, 7, 8. Since 8 and 5 are connected, we can move between those. We keep on moving between the adjacent tiles until we reach our goal. And down here is just showing you what the source of each tile is.
Is it weighted as one file or 1.7 for another?
No, for breadth first search, we don't weigh. Yeah. Okay, for mapping, we need to map all the tiles. The way we represent our data is we represent each element in our array as 1/4 of the tile. So right here, this would be one tile, but one element would be 1/4 of that tile. And the reason why we did that is because, as you saw before, there are half walls. So it's not always going to be a tile by tile. So they could be split in between the tiles. So that allows us to use the same algorithm between all 3 rooms. And it makes it a lot easier for mapping so that we don't need to change our algorithm when we need to go into a different room.
Sorry, question. You said the half wall, what's special about the half wall? It's not on the boundary of
Yeah.
time?
So this is just a picture of what would look like in a room 1, but a room 2 could have a wall like in between here. Or like,
In between 6 and 7.
yeah. So like you could have, like it could just be half of that.
Okay.
So it would be much more complicated to represent so many different wall positions if it was just one whole tile. And we store different properties in our array. If there's a wall on the north, south, east, and west, whether this tile is visited or unvisited, by default, all of it is unvisited. But then as we go on, we say we visited it. And then we also store the floor color. So we can have normal floor color and then label whether it's room 1, 2, or 3, and 4, and then swamps and black holes. And that will come useful when we come to the map bonus, which is next. So another thing with this competition is that at the end, you need to send in a map bonus matrix. So on the right here, that's an example of what one would look like. It's basically like a bird's eye view of what the maze look like. So just the ones are labeled as walls. 0 is just the ground. The fives there are just labeled that there's a start tile. So you need to label the walls. You need to label any victims that you saw. Also floor color. So that's why we need to store the floor color in our array, because when we send in our map, we need to fill in, oh, if there's a checkpoint here, if there's a black hole here. And then the neat thing about the map bonus is that you can basically double your score at the end based on how much percent correct your matrix is. So the way we did this is we allocated a static 100 by 100 string matrix at the beginning. And then at the end, since we're keeping track of how many tiles we're visiting, we can just calculate the size of the matrix that we actually want to send, because we can't just send the full 100 by 100 or else we won't get a good percentage. So then what we do is we just create a new matrix with the calculated size, and it's basically just cropping it down so that we just send in the size that we want to. And then from there, there's a device we use called the emitter, and it basically gets to talk with the simulation server. So it's very useful if we want to get like data like how much time is left or stuff like that. So we could just send in our matrix to the simulation server, and then from there we can see if we got a good percentage or not. Yeah.
What's a black hole?
A black hole, can go back to,
Yeah.
it's kind of hard to see that's a black hole. So it has like a black outline, and if the robot isn't being careful, it can fall in, and then you wouldn't want that, because then it would have to like go back to like a checkpoint. So these silver points are checkpoints here. So
The
you,
robot will quite literally fall straight into.
yeah. So there's a difference in the level. It's literally just a hole. So it will just, yeah, it would just fall through. Yeah, so the way we fill in our map, first, when we visit our tile, we perform the LiDAR scan. So we want to check all 4 directions to see the walls. And then this is our tile structure. So they're all in an array. So in this case, north would be set to true here, north and west, true, and then east and south would be false. This is a checkpoint, so we mark the color as a checkpoint. And then from there, we fill in the values in our string matrix. So we fill in the 1s, and then since it's a checkpoint, we fill in that it's a 4, which is just the code for a checkpoint. For victim and hazmat signs, it doesn't, the way that it works is that you have to shift it based on what side of the wall it's in. So since this S is shifted to the right side, we had to map the S in on the right side there. So for this, we had to look at the rotation of the robot with the IMU, and then from there determine what side to fill the S in. For victim detection, I'll be Andrew Chen took care of the victim detection, but I'll try to explain it to the best of my ability. So the first thing we do with victim detection is image processing. We need to remove the blue wall background at the start and threshold our image. So we need to threshold our image in order to do something called finding our contours. And for that, it needs to be a pure black and white image. So first we have to convert our color RGB image. So before all this, it looks like normal, like how you would see it. And then we would convert it to a grayscale image. And then after that, we do another threshold to get the black and white. And then the reason why we removed the blue wall is to get the region of interest. So we don't want to look at the whole picture. That's just like a small sliver of what we would see in the camera frame. It's like a 128 by 64 image. We just want to see like the hazard or the letter. So we remove the blue wall, and we can see anything that isn't blue, it's probably a sign. So we can do some we can see like the area of that. And if it's like a big enough area, then we know it's probably a hazard or a letter. So this would be kind of what our region of interest is. So that's what we want to look at. For hazards, one key way to determine if it's a hazard rather than a victim is a hazard is tilted 45 degrees. So that's an easy way for us to determine whether it's a hazard or a victim. Now between these four, we can easily see that flammable and organic peroxide have both red in it. So we can check if our region of interest has any red in it. It's definitely not these two. It has to be one of these. And then from there, we check if there's yellow. Yellow, it's organic peroxide. And if there's no yellow, then it's flammable. Now for poison and corrosive, it's a bit trickier because they're both black and white. But what we did is corrosive has like a lot of black area, like it takes up more black in the frame than poison. So we can just compare the ratio of the black area to the total area, and if it has a greater amount, then it's corrosive. If not, it's poison. Victim detection. We used a simple method for victim detection, but it proved to be useful and effective in our case. It's called the slicing method. So basically we take the 3 slices of our image, and then we count out how many like black strips there are. So here the H has 2 on the top, and 1 in the middle, and then 2 on the bottom. The S has 1 in each, and then the U has 2 in the top and middle, and then 1 in the bottom. So based on how many are in each, we're able to determine what letter it is.
H and one, what does it mean?
Like 1 black,
Contour.
yeah. So
Not interrupted, yeah.
Yeah.
Which is one big thing.
yeah, it's 1 chunk, and then the 2 is just 2 separate lines there.
Letters represent.
In this case, I think it's harmed, safe, and unharmed.
So the robot sends back a specific code based on which type of victim it is.
Yeah.
And that's how they get the points for it. If they get the wrong victim, they don't get as many points. So it's important to differentiate.
All right. I'll be talking about our room 4 protocol, in which we used SLAM. There's 4 sections to this part: data collection, how we build our map, how we navigate through the map, and finally our movement. So let's just first go over what SLAM and LiDAR are. So SLAM is basically SLAM stands for simultaneous localization and mapping, and it's basically a process that a robot can use to navigate through a new environment. So think of like a Roomba exploring a new room in your house. It doesn't really know where it's going, but as it goes around, it can sort of figure out where it is and slowly build a map of what that room looks like. So figuring out where it is in that room is the localization part, and basically adding onto that map so it gets a better idea of what's in that room is the mapping part. In order to do SLAM, there are many different methods. People can use cameras, depth cameras, but one thing that we decided to use was the LiDAR. So the LiDAR that we used basically provides us with a 360-degree field of view distance measurement around the robot. And the way it does this is it basically takes a laser scanner and it spins it 360 degrees to get a bunch of data point measurements. And you can see that in that GIF over on the right. You can see the scanner up in the top rotating, and the laser taking measurements of distance, which can be seen down here. So we decided to use the LiDAR for our data collection because it provides us with this full view, and we can keep on building these scans to produce one large map. Because the room 4 is so random, in fact, that we had to make like a new room 4, since it's completely random, we actually just draw like squiggles in paint and make shapes using like Google Drawings. And that's how we test our room 4 and build maps for this area. So basically being able to traverse this area, not randomly, but with an idea in mind, being able to map out exactly where we are and explore all the areas was very important. So having like a 360-degree field of view was really useful. So data collection. So one example of a maze in a WeWat simulated environment and like a resulting LiDAR scan is shown over on the right. And you can see the points just produced by the LiDAR. So another example of this is right here in a sample room 4 area. So at this blue dot right here on the scan, which is where we took the LiDAR scan, which is about somewhere here on the actual map. And you can see that the black points form lines that basically look exactly like the room. And you can see that we have these little red dots, which I'll go over what the purpose of those are. So now that we have a LiDAR scan, one of the big challenges is how exactly we stitch them together. For example, if I take a LiDAR scan over here and one over here, how do I know where to combine the different points such that it builds a cumulative map? So I'm going to go through an example right here. For example, if a robot were to start up in this top right tile, move along to the left and stop over here, go down and into this little area. If we took 6 different LiDAR snapshots at this point, which I'm going to show on screen, how exactly do we stitch them together to make one big map? So right here are these 6 LiDAR scans. You can see we start here at the top right. The blue dots signify where exactly the LiDAR snapshot was taken. And this is just following this path right here. So take a moment just to try and figure out like where these LiDAR scans were taken and stuff like that. So we can see that the robot progresses from left up here in the top left over to the right, goes down a little, and then into this little like area with curves. And the way that we basically triangulate between these different snapshots is by finding key points in our LiDAR snapshots. So what do we define as a key point? Well, basically, it's a feature that we can find across multiple different LiDAR scans. For example, if there's a corner in a specific area, and we see that corner in 2 different places, we can essentially triangulate where we are based on the fact that we know where this corner is. So we essentially detect these key points by finding a sudden change in the rate of change of the angle between every set of 3 points. So for example, if every set of 3 points is producing a 180-degree angle, and then we suddenly see a 90-degree angle back to a 180-degree angle, that indicates to us that there's some sort of feature there that we should know about and we can use to triangulate our position. So up here in the top left, we can see that there are 4 of these green dots, which match on our second scan, which was taken towards the left of the original scan. And by essentially triangulating where these points are, we know we can try and figure out how to stitch these together. And you can see that these points go all the way from the top left to the bottom right. For example, these orange and green points from previously are present in this LiDAR scan, and these points keep moving along until the end. And essentially, as we keep finding these points and keep traversing through the maze, we're able to triangulate and localize exactly where we are so that we're able to combine these snapshots effectively.
I noticed before you said you had a GPS on board. Is it that the resolution is it you don't have as accurate? Because in theory, couldn't you use that to know when you're using GPS to know how far you've gone and then?
Yeah, so we did use the GPS in combination with this method. It was more like if the GPS starts to drift and we have issues with that, because that's something common. Normally, like a robot like this wouldn't be able to just tell where it was, like the simulation.
Indoors and stuff.
Yeah, so this was kind of set up in combination with the GPS readings to maintain accuracy. All right, so now let's take a look at what this looks like when we combine these snapshots now that we know exactly where we are. So in this maze up here, we just had the robot drive straight through down that top alley. And we took LiDAR scans at these pink points. And when we combine these LiDAR snapshots, basically based on the key points we found, you can see that we get this kind of accurate, but also at the same time, kind of noisy data set that resembles the map. You can see that there are some inaccuracies, for example, up here where we have points sticking out. And we'll discuss how we address this a bit later. Actually, right now. So, so when we look at when we look at a line like this one in the simulation, when we zoom in on this line, what we actually notice is that it's not composed of straight dots after a point. After a point, the noise starts to kick in and get a little annoying, and we get some sort of formation that resembles a line, but isn't exactly a line. So in order to combat this, we developed an algorithm that determines the accuracy of points based on the angle at which the snapshot was captured and the distance at which the points were captured. So if we go back to this first scan, I know the image on the left doesn't exactly match the one on the right, but if we take a look right here, we can see that the LiDAR scan was taken right here. And as the angle of the laser approaches the same angle as the wall, points start to get inaccurate. And as points get further away, we can see that they get more inaccurate. So based on this, these two pieces of information, we developed an algorithm for determining the accuracy of our points that we take in our scans. So right here is a heat map displaying this accuracy algorithm, where the redder points represent inaccurate points, and the warmer points represent inaccurate points, and the bluer points represent the more accurate points. And you can see that the blue points form like straight lines, whereas the red points, you can see they're getting a little inconsistent. Just to take a better look of what this looks like, I'm just going to zoom in on this portion right here. And we can see that the bluer lines, the bluer points form straight lines and accurate representation of the walls, whereas we can see the red points are really inaccurate and capturing the same walls and would mislead us basically if we tried to combine them. So now that we can eliminate our inaccurate points, yeah.
So how come you have both red and blue here? The red ones from previous scans?
Yeah, so this is just a zoomed in portion of this this set of readings. So you can see there's a bunch of pink circles, all of which represent LiDAR scans. And just zooming in on this portion right here, this is the same part, but yeah, that's probably from inaccurate scans from up in the top. And yeah.
How do you like know if it's bad? Is it like based off of distance? Like if it's this far away from the sensor, then it's questionable and
Yeah, so
waiting or something.
yeah, so it was based on two factors. One was the angle at which the LiDAR like scanner took the wall. So we found that if it was like 90 degrees and the LiDAR scanner was taking the wall, it would be fairly accurate. Whereas if the LiDAR scanner was over here and we had a wall like this, as the angle of the LiDAR approaches the angle of the wall, it would start to get more inaccurate. And also as it gets farther away, it's also more inaccurate. So using both of those ideas in mind, we developed like an algorithm to determine the accuracy.
That's a simulation, so I guess you don't have access to how the code calculates this radar.
Yeah, not really, but we have like noise variables that we can adjust to if we wanted to add more or less like noise to our
The LiDAR coding, I think what you need, LiDAR is just a physical sensor. So like,
No, but in reality, depending on the type of wall that you have, whether the headphones or things like that.
yeah,
So that's, you don't have that in it, right? You don't have reflections and things like.
No, I mean the walls aren't like a reflective surface, so that's not something we have to worry about.
Because if it were a perfect mirror, you wouldn't get anything back.
Yeah.
it was like a window or something.
Yeah,
Well,
We don't have to worry about it.
yeah. All right. So now that we have like a bunch of data points, how do we combine them to build this map that we've been talking about? So at first, we just tried to simply combine every single point and take a bunch of LiDAR scans as we went through it. And you can see that the path the robot took with the LiDAR scans. Unfortunately, while this does produce like a decent map, this scan, for example, had like hundreds of thousands of points or tens of thousands of points. And simply, if we wanted to say, check if there's a wall over here, we would have to sift through all of these thousands of points just to check if there was a point at a certain location, which is obviously extremely efficient. So we need to find a way to get rid of the duplicate points and develop basically a data structure that's able to hold all these points in a way that is fast to access, fast to modify, and robust. So the way that we did this was by splitting up our points in a tile system. So if these were the walls, for example, of a maze, if we wanted to access points in this region, for example, if we wanted to check if there's a wall in this region, we wouldn't have to look through all of our points. We would only have to check like right here, sort of like an index. So with this in mind, we created a algorithm to check if points were duplicates using this data structure. And in the end, we have a completed map, like a 2D point cloud of this map on the right. And you can see that even features like the thickness of the walls are represented in the map on the left. And there's some places like right here where we don't see part of the wall. And that's just because the robot was unable to access that part of the maze. But you can see that the points line up pretty much perfectly with the map on the right. So now we have a way to build a map. How do we exactly move through it? How do we navigate and how do we explore all the parts of our maze without getting stuck? So in order to navigate, at first, we decided to try and use our tile-based system that we use to store the map to navigate. So for example, if we take this tile right here, which I have made a bit larger over here, we would try and determine which directions we could come to and from, depending on which parts of the tile we essentially came from. So if we came from the left side of the tile, it would be possible for us to move up and down. Unfortunately, this solution doesn't really work because there are a lot of edge cases, like for example, walls laying on the edge of two different tiles. There are also issues like, although it may seem based on the gap that it might be possible for the robot to go from this region to the left, it may not actually be the case because there may be walls in different tiles that won't allow that. And it's just difficult to split up such an organic problem like this into like certain divisions because I mean that's not like a correct way to approach the problem, I guess, since like the problem of the maze is so random that splitting it up into sections and trying to figure out a way to navigate from tile to tile is just simply too difficult. So we went back to the drawing board and we developed a second navigation algorithm. And although it may look scary, I'll go through how this works. So we have our first, I don't know if you guys can see that, but up here we have a light blue wall, and this just represents a goal wall or like an unvisited wall where we would want to check for victims on the walls. And next to it is our goal position, so we can trace along the wall and discover this new area. The pink circle represents our current position, and essentially the way this algorithm works is we directly try to go from the pink dot to the goal. So we go directly from the start to the goal. And if there's an obstacle in the way, essentially if we can't move forward that amount of distance, we try paths in increasing angles until a new viable path is found. So the way this would work is we would start at the pink dot, and again, we just try to go forward towards the gold star, which would lead us to right here. At this point, we make a waypoint, which is essentially like a midpoint that the robot can use to navigate to from the pink circle to the gold dot, to the gold star. And at this point, we can also move forward one more time. But at this point, we are blocked by the wall. So what the robot would do is try to move forward at increasing angles. It would try a path at 5 degrees, 10 degrees, 20 degrees, and so on, until it's able to find a path right here at about 120 degrees. And also a path at the left at about like 110 degrees to the left. At this point, this process just keeps on repeating. We keep starting at the previous waypoint, and we keep trying to move directly to the star while turning to avoid any obstacles. So what essentially happens is we create a path where we go forward, we go around this wall. We again, now we can go directly towards the star, so we try to. And then when we encounter an obstacle, we again go around it and we go directly towards the star. This results with 3 different paths. You may be wondering why this path is blocked off. That's simply because the robot checks if it can actually fit through a gap like that. So we are left with 3 different paths, one that goes up and to the left, to the right, and then one that goes all the way along if the path were continued. So now that we've generated basically 3 different ways to get from the start to the goal, we just simply pick the shortest path, which would be right here, which would be this path right here to the star. So let's see this in action. Using this previous maze, using the previous maze from before, if we wanted to navigate from a position like here, over to down in the center here, let's see what this navigation algorithm comes up with. And you're just going to see the waypoints to move to that goal. So right here, the red dots are the waypoints representing basically the path that the robot should take from this starting tile to the goal tile. And you could see it doing this process. It tries to go towards the goal, but has to make a slight turn. At this point, it can go directly towards the goal, so it does. And then again, we have it going directly towards the goal and then moving around until finally it finds a path. So now you may be noticing that this isn't the most efficient path. For example, in this path right here, in our shortest path, there's no need to go directly up against towards the wall and then go back. We could simply just go directly right here, right? So the way we tackle this is by essentially treating every previous waypoint as a new goal. So we take this gold star, now that we've navigated to it, and we eliminate it. And we take this previous waypoint that leads to the gold star, and we treat that as the new goal, like target. And what happens is we end up with essentially dots like this, which can be simplified by going directly to them, being optimized, and even points like right here, we go directly to them. And as we move basically down the line, we get a new optimized path. And you can see that signified by the blue over the top of the red in this diagram.
You calculate both, and you start by calculating the first one, and then you refine.
Yeah, so we first calculate a bunch of different paths to the goal, pick the shortest one, and then we treat every previous waypoint in that as a goal to optimize it. Yeah. So now that we have actually, now that we are able to generate a path, how do we actually move? So when we generate a path like this one, we simply move from waypoint to waypoint. It's pretty easy. We just drive to the next waypoint, change to the next waypoint, and drive, and so on. But keep in mind, this navigation algorithm is kind of expensive. It takes some time for the robot to generate this path. And we wouldn't want to be doing this, for example, in a maze like this one. In a maze like this, we wouldn't simply want to, so the goal of the competition is to discover the entire maze. And if we were at a position like this, where everything around us is completely novel, there's no need to navigate to a point like 1 meter in front of us, right? So in order to do that, in order to accommodate for that, what we do is we simply wall trace whenever we find a novel wall. So when we wall trace, we use the LiDAR again, and we use 2 rays of the LiDAR since it has a 360-degree scan. So we use a PD controller, and by default, it uses this front ray to trace forward, and this back ray as a backup for sharp turns and sharp curves. So when the wall in front of the robot starts to shorten, the front ray, and the distance between the two is shorter, the robot will turn to the left. And when the distance is a little farther, it'll turn to the right. In a certain case, like a corner, once the robot is, so if the robot is moving forward, the front ray would eventually just completely miss the wall. And at this point, the back ray starts to trace. And once the back ray starts seeing that the wall is a little farther and farther away, it will eventually take over by turning to the right. And then this process would repeat until the front ray latches back onto the wall in this like corner, for example. So let's take a look at what this looks like. Here's a GIF of the robot just driving around using this wall tracing algorithm. It's just driving around the obstacles, and whenever it sees a wall in front, it's just simply turning around it. And you can see that it's exploring pretty much all the areas it can while guiding to the right. All right. So now, obviously, we have a lot of different processes like victim detection, our SLAM, and stuff like our navigation. So how do we test and make sure all of this works seamlessly every single time? So the first thing is to test with two different complexities of worlds. At first, we have sample and easy worlds. We use these as controls and sanity tests whenever we make changes, just to make sure nothing has gone completely wrong and that a robot doesn't completely fail. And then we have the harder mazes, which is where we really test new parts of our code, like obstacle avoidance and like over here, maybe curved walls. So in order to rank how our robot is doing with new changes, we have a performance metrics table. And basically the way this works is we take a bunch of test worlds that we think are useful, and we rank our latest changes on this system. So we have a best score of all time that our best like our best version of our code did. We have our latest score from our latest changes, and we have the total in some cases we have the total possible amount of points, and we also have a section for our map correctness. So that's the thing that Peter was talking about at the end, where we send over what the map looks like to the just to the simulation software. So for example, if we look at Obstacle Alley over here, we were scoring 0 points, and if we want to know what went wrong, we can look at our notes and it says it's too scared of the obstacles. So the reasons why we did this was to measure how well the robot's doing, measure different aspects of a robot, like the map bonus percentage and how that's doing, and also track stuff like how much time was left, whether this version is faster or slower than previous versions. And having control tests and sanity tests would help us like make sure that revisions weren't completely breaking everything, and also different worlds designed to test specific actions like obstacles or curved walls helped us isolate issues. So now you can see a video of our robot just going through a maze. I'm going to speed this up in double speed. You can see it detected a victim right here, and it's just going through. Now it's entered a swamp, so you can see it slows down a little. But yeah, it's just going to go through the entire maze, finding all the victims and stuff. If you have any questions, we'll take them at the end of this video.
What's your question?
Okay.
Any question?
Yeah. So this is the room 4 portion of the robot. So you can see it wall tracing around and finding all the victims.
Oh, if anybody's curious too, you get different points. There's actually a multiplier, so you get less points for getting things correct in room 1, but then you get, I think, 1.25 times for room 2, 1.5 times for room 3, 2 times the score in room 4. So it really becomes beneficial to go through all the trouble of navigating room 4 because you get a lot of points there.
So what's the language you're trying
The language, we're doing C++.
Oh yeah, actually. So yeah, so all of our code that runs the robot was written in C++. But a lot of the SLAM stuff that I worked on, just because of its complexity, I wrote it first in Python, and then just rewrote it again in C with some optimizations and stuff. Especially some of those diagrams that you saw of those point clouds and heat maps and all of those little diagrams. Those were all generated in Python using like plotting libraries.
Much harder to do that.
Yeah.
So with the room 4 where it's mapping, so you do your wall tracing and then you use the algorithm where it like has a specific goal point to drive to afterward? Or...
Yeah. So when we start, we just start wall tracing, and basically if in our map we find that there's an unvisited wall or like a location that we can go to, then the goal like kicks in.
Oh, because it's tracing around and it's like, oh, there's a spot we missed here. Then
Yeah.
Okay.
So yeah. All right. Good.
So some of the algorithms that we use can be found on the web document.
References, yeah.
Are you allowed to take that, or you have to put it yourself?
No, I mean, yeah, I wrote it myself, but like, it's not like my original idea. It's used.
Right, I mean, it's long.
Yeah, I mean, I think it would even be kind of difficult to just copy it online.
Yeah.
And try and use it for the competition, because I mean, you have to really know in depth like how the algorithm works, how you're applying it to the problem and stuff. You can't really just take an algorithm from
I
online and
guess
try
the
and
question is,
apply
are
it.
you allowed to use external libraries?
So you're allowed to use certain external libraries like OpenCV for image processing, but stuff like, for example, Tesseract or like machine learning libraries that you can use too, or like OCR software basically is not allowed because you'd be able to
Oh,
identify like
That's what
those.
Tesseract.
Yeah.
You could basically give them, that's how you right away, oh, that's an image.
Yeah.
You can't use that, they had to figure out how to find the images with them. By the way, Dhruva did most of that slime work by himself. I helped as much as I could, I was there, but he really drew it, he was like the driving force behind all that, and all those images he documented all of this.
I'm going to be a senior.
Yeah, we're both gonna be seniors.
How big is your team? So totally for this, with the robo.
There's 4 of us, so
Can you go over why? Right, because you know, it doesn't run quite.
it can, but the problem is with Python, doing all of that would be pretty slow. C is just much faster for this kind of thing.
That's an experiment too, we put it in chat, translate it.
How easy is that?
Yeah.
I mean, they have surprises like when we run during the competition, and imagine that it's uploaded to some computer. Runs the program, right?
Yeah.
So does it run faster, does it run slower?
Well, so the way they did it was there was like they would run the code on their own computer, but then there was another computer there on site that would do the actual simulation calculation. And it wasn't really the best computer, I guess.
Yeah. Oh, we found that when we were running it in France, the computer was like a lot slower. It actually ran slower than like 1x speed. So what would happen is when we were running it, we're able to like check the simulated time. So like we have like a last resort option. Like if we have like not so much time left, we're gonna try to go back to the start and like try to end the program. But the thing is, since the simulated time was running slower than the real time, so there's 8 minutes of simulated time limit, and then there's 10 minutes of real time. So what would happen was the real time would run out faster than the simulated time. So we actually can't tell unless we're like checking for the real time, and then the simulation would end before our program ends, basically. So, stuff.
This is huge difference, because you don't have a chance to send it from this map back.
Yeah.
This is huge.
Oh,
Yeah.
Yeah, you really benefit a lot from getting back to the start tile and sending it back.
Yeah.
The whole purpose of sending the map back is to make sure that you guys know any chance that you do a part for the map, and then also hopefully that when you send the map back, then you really can exemplify everything you have seen, like a snapshot.
You didn't get a chance to go back.
Yeah.
And also that really cool to see that is that because they are supposed to recalculate the path to use the forest path to get back, so that it's not the same as the way we follow. Like for example, they have your blue tile, purple tile, long tile, things like that.
Yeah.
Yeah.
But we're not going to get into the backside of the game, and this year was a part, I'd say. But I mean, I was very much into it because I thought organizing, so I kind of know myself, but also I'm not there. I was not there. I never go to compete. They
Too much
just
stress.
so big. It is, and then all this is their game. If I go there, then it's not that I can help them. I'm not allowed to talk to them. As a matter of fact, I can talk to them more when I'm here. Because I'm serious. I went there. I got Poland to help everything else, and then I was so absorbed that I had no clue what to expect the next day. And a lot of times in law announcement, I missed the announcement because I was so absorbed in helping everything else there. This year, luckily I was here because they were so It is difficult to run international game to begin with, so I'm not gonna say anything bad about that as like, they did all of it, I have to say. But anyway, so I guess they taking a lot more they can show this year, and if I was not here, they would have missed the talk. Because the American came up so late, something, 3 o'clock in the morning, when we saw my phone, I was like, oh my God, it's the announcement, 3 o'clock French time, stop it. Yes, and then look at, oh my God, I'm caught up and then go to talk to this, hey guys, guess what, you have a talk's coming up, right? And then so this guy is like, just whip up really quick, put things back together and then do a presentation. I got a nice email from the organizer, they said that it's gonna be a wonderful job and then they will give a great nice praise, so we just kind of.
Is that the presentation of the?
Yeah.
Is this like an annual, like, you know, how many hours is this a job for? Not to get, you know, is it an annual, a year-long effort that you guys, plan to do?
I think we started in the fall, but we didn't officially form the team until like January, around there.
But we did, so you been doing your main stunning videos. How many years have you been doing it?
I did it this year and then I also did it last year, but I was doing the victim detection last year.
Oh, but you could sort of improve on the ideas that they have.
Yeah.
This is my first year of
First is starting
simulation.
January.
Yeah, but I've done rescue maze for 2 years before this.
So this particular.
No, I just wanted to know, we still have school work to do. Right?
Yeah.
So you're in school band, forget it. They're like a school band, it's like quite so much of our time, right? And it's just too much pressure. But yeah, this is kind of it's a lot of this.
So this particular competition is that just about names, but the names changes every year, because I think it's like we did it for the last year. Sorry, I just came in, knowing nothing about. Is this a particular competition, is like names?
Yes.
Topic is names,
Yeah.
but each year the names go up. Because they're putting the.
Well, yeah, they
Yeah.
update the rules. They also did something which I don't necessarily agree with, but the obstacle down there is a cone. They just like threw that out
Yeah.
there randomly. And like, that wasn't how anybody's been using it. So they will change it sometimes sporadically. But yeah, it changes, they update it, they change the rules.
Yeah.
They've already posted something about rule changes that they propose, which there's like, here, for example, at least this is what Peter was telling us, you can really only go from room 1 to 2, 2 to 3, 3 to 4, 4 to 1. But now they're gonna make it so that, you know, you can go from room 3 to 1, 2 to 4, totally mix up. So already it's a change. Issue.
Wait, that's the point of the color.
Yeah.
Yeah.
The robot is about to go from room 1 to room 3.
No,
Yeah.
it couldn't do that in the past. So the blue tile there is from room 1 to 2, and the
Yeah.
top right to the bottom right, and then the purple is from room 2 to 3, and the red is from. 3
So
to
based
4.
on what color we see, we're able to determine what room
I
we're in.
think that,
Like, once you
the
expect,
there,
yeah.
you could go directly into room 4.
Yeah.
That green.
So
But
basically,
if you see
you're
that,
not allowed to.
robot see that, you have to back up and-
Yeah.
Yeah, if you don't have room 4,
Yeah.
And I said, let me elaborate, I think exactly, I think like a parent.
Exactly.
So I think exactly what she's looking for, she's looking for, like, there in the United States, this is extremely unique game. And, like, let's say take Garrett and whatnot, their games change every year, they literally have to invest a 20,000, some plus on the field, the whole setup is different. And, but this doesn't really change a lot, however, it's extremely difficult. One, it's fully automation. You cannot just like remote control. That's one. And second thing is the field maze, however, the setup is totally different. So you have all robots, there's no way to parkour anything. You have to be smart enough to instantaneous take a variable, a huge less variable, which is kind of unknown. So to be able to handle the situation. So they can't really change it every year. There's another beautiful thing about it. You don't have to spend a lot of money to get a lot out. Right. That's a big difference. And also this, besides we did other needs too, based on the candidate, the interest.
But, again, that's kind of that, if you were to commit to, it's a high school, right? That's another thing. If you were to commit to set it off?
Yeah, so I'm in the marching band, which is basically like we take like 30 hours a week to practice. Yeah, that's true,
So
but
would you be able to do this in the fall?
yeah, definitely. Yeah.
That's him.
Yeah.
This is like.
Yeah.
They do stupid, but anyway,
Yeah.
he's market. So you have that mind.
Yeah. I mean, if you've been doing this for like some time, and it's a lot more difficult if it's like new to you, I guess.
Spring, like, so you guys are-
Yeah.
Say, Peter, right?
Yeah.
Peter, that you guys formed the team in spring, and this competition is like what, in summer? So
Yes.
this was-
Yeah.
So spring sounds like, you know, the time where you really invest and spend time on it. Did you have the time to do school sports? Say track. I want to be specific, because I want to ask just on the happiness, right? And being a competitive, sport, would you think it's possible? Feasible?
Yeah, it's definitely possible. It's
I know a friend at school who was on May's team here actually, and he was also doing some track stuff. But then, especially when it became crunch time, right into the days of the competition, like the weeks before, where you're coming in like usually after school, you sort of then have to think, are you going to really be dedicated on the robotics stuff, or are you going to still go to the track meets? He chose to go to the robotics stuff, so he didn't go to track for like a couple weeks. I guess it just really depends on also like your school classes, and like at the same time there's AP stuff, and so you have other exams. It's just about budgeting time. And
yeah, I mean, another thing is a lot of teams also start in the fall. So if you've had that prep for that like additional term, you'll be able to it'll be much easier in the spring.
Easier, it's still hard.
Yeah. And also, like, what is, like, you two are incoming seniors, right? Are all four incoming seniors?
No.
No.
Andrew Chen is gonna be higher.
Yeah.
So it's the
So two younger ones, two.
Yeah, and so I mean, throughout the year, it was like a minimum of 2 hours a week. But by the end, by the last couple of months, or like the last month, it was what, probably like 10 hours a week.
Yeah.
Yeah, and then we had meetings too.
Yeah.
When was the competition? Because I was looking for online, but I don't think I find it.
It's mid-July.
Did you say?
Oh,
The one during the year.
Yeah, that's
End of May.
May.
End of May.
What did you guys were talking about, you were in France, right?
Yeah. That was for
So
the
the
July.
In France, that happened, that last one was in July.
Mhm.
You say it's all worth it, spending the time.
Yeah, it's a lot of fun.
Yeah.
We haven't spent time with you, so.
So both of you informed to your team, they've been with, like, this is, you guys have been installing robots for several years, how long?
I've been here
Mhm.
since like 6th or 7th grade, I think. Yeah. So yeah, it's been a long time.
Yeah. Six.
I don't even know that he was not shorter. They both were not shorter than me that time.
The book you're applying for computer science for colleges.
Yeah.
Again,
In here, you usually pull kids like that down to like the 12th grade, to do another competition, unless they really wanted to, but I just, I don't encourage that. I usually encourage them to do the really bad part, into the independent part. So then now
both
it's like,
with a lot of application stuff like that. You know,
yes,
it's not going on.
my next time, we'll get into that about the value of the projects.
Great job, guys.
Yes.
Thank you, guys.